In this lesson, we will try to determine the difference between a relation and a function, and we'll begin learning a variety of things that we should understand about functions. So to begin with, if we can describe one quantity in terms of another, that means there is some sort of relation between the two. In other words, you could make a pairing between two things. So, for example, if you look at the blanks, the letter grade you receive in a mathematics course would depend on your numerical average, would go in that first blank. Your numerical average would determine your letter grade. Now, next one, the amount you pay for gas at the gas station would depend on the number of gallons pumped. So the amount that you have to pay will depend on the number of gallons you put in your tank. And in the last blank, we could see this type of relationship. The dollars spent on entertainment would depend on and let me give you a quick example so you can see. Would you expect to pay the same amount of money to go watch a movie as you would pay to go to Six Flags? Probably not. Therefore, the dollars spent on entertainment would depend on the type of entertainment. So it all depends on what you're choosing to do, what you would pay. Therefore, we get to a definition for a relation. It is simply a set of ordered pairs. If it is possible to pair up items, now notice it doesn't even have to be exclusively numbers. You can put a pairing together of things where maybe they're categories of things. You could look at a budget, and so a category for a budget item could pair up with a particular dollar amount, and that's still a relation. You have a particular relationship between those. Most of the time when we work with these items, we will probably be looking at sets of numbers. So if we can form an ordered pair, we have a relation. A function, however, is a relation in which for each distinct value of the first component of the ordered pairs, there is exactly one value of the second component. Now, here's what that means in practical terms. When we think of ordered pairs, remember that the x comes first, the y is second, when we think about putting together ordered pairs. So what this is saying is if we're looking at ordered pairs, we look at each x value in the ordered pairs. If all of the x's are different, we're going to have a function. The only time we're going to have a problem is if we get the same first component, the same x, going to two different y's. So if we ever see an ordered pair where the x value is repeated in more than one ordered pair, it won't be a function. So let's look at this example where we have some sets of ordered pairs and we have to determine whether the relation defines a function or not. So in set M, if I check these ordered pairs, remember all I have to do is simply look at the x values. I really don't even care what the y values are if I'm trying to determine if I have a function. So the first one is -4. The next ordered pair has an x value of -3. The last one has an x value of +3. That's all I have to look at. Those numbers all are different. Therefore, it's a function. As long as the x's are different, I don't even care about y's. I'm just checking the x values. Look at set N. Evaluate those ordered pairs. Are the x's all different? Yes, they are. That means it is also a function. Now, when you check set P, do you see a problem somewhere? Hopefully you do recognize that we have an x that's repeated in two different ordered pairs. -4 is paired with 3 in the first ordered pair, but in the last one, -4 is paired with -3. Because the x value was repeated with two different y's, it is not a function. And that's all you have to look for with ordered pairs to determine whether or not you have a function. So here are a couple of ways that we can describe what we just did, what we just learned and we practiced in that example. In a function, no two ordered pairs can have the same what? We said it was the same x value. No two ordered pairs can have the same x value and different y values. Very important. Check your x values. As long as they're all different, you've got a function. If they are repeated, you won't have a function. In a function, there is exactly one value of the dependent variable, which is the second component. You may want to put in parentheses, that means it's the y, for each value of the independent variable, which is the first component, and in parentheses you might wish to put an x out there to remind yourself that that's what that means. So we're just introducing a little more vocabulary. That's another way you can think about what we just covered. Let's move to the next slide. We're now going to cover the terms domain and range. In a relation consisting of ordered pairs, and we know that the ordered pair, the x comes first, the y is second, then the set of all values of the independent variable x is called the domain. So if we list all the possible x values in a set, we have identified the domain. That means if we were to list all the values of the dependent variable y in a set, it is called the range. And you will be asked to identify domain and range, and is it a function for a variety of things in this section and on this chapter test. So let's look at a few more examples. Now we're not only going to answer the question, is it a function, but also identify domain and range. So if you look at example A on classroom example 2, it's a set of ordered pairs. Let's review. What is our test to see if we have a function? All you have to check is what? Your x values. Are these different? Yes, they are. If I look, I have a -4, a -1, a 1, and a 3. Because they're different, that tells me it's a function. Now, to list the domain, I'm going to put inside the set notation, which means I open up a brace. Please don't use a parentheses. You need to use a brace. And we will separate these individual x values with a common. So I have -4, -1, +1, and +3. And then I close off the set. Now for the range, I'll do the same, but I'll list y values. So I open the set, I go back and I look at the y's, and I'm going to have -2, comma, 0, comma, 2, comma, and 5, and close my set. Now let me just mention a couple of things here. The order you write these in really does not matter. Oftentimes you will see them listed from least to greatest, but they can be in any order. So don't worry about the order you list those values in. The second thing I want to mention is if you ever see a value that's repeated, if we had an ordered pair, for instance in this example, if this 2 right here had actually been -2, which we had already listed, we wouldn't write it down again because we're listing all the different values that could be in either the domain or range when we're making these lists. So don't repeat numbers. In the order you write them in won't matter. Let's move on to example B. What you'll notice is these are not written as ordered pairs. Instead, this is called a mapping. And if you follow the arrow as it leaves the oval from the left, it will show you what the y value is in the oval on the right. So really, when it comes to identifying domain and range, this example will be very easy because the x's are already separated into the first oval, the y's are separated into the second. Now, in answering the question, is it a function, remember our test is, are there any x values that go to two different y's? Well, that means when we look at these ovals, you need to check to see that you do not have two arrows leaving from the same oval on the left. And if you'll notice, that occurs right here. We have a problem. If we were to put this where they were written as ordered pairs, one ordered pair would be 2, 5, but the other one would be 2, 6. That means it's not a function. It wouldn't matter if I have two arrows pointing to the same number in the right oval. I just can't have two arrows leaving the same number in the left oval. Now, to list the domain, all I have to do is identify all the possible x values. That means it's 1, 2, 3, because that came from the oval on the left. For my range, those are the possible y values. That comes from the oval on the right, 4, 5, 6, 7. Look at example C. These are not written as ordered pairs, although we could easily put them as ordered pairs. Instead, it's written as a table. But much like the last example, our x's are already separated from our y's, so domain and range should be simple for us. How do we decide if we have a function? All we have to check would be x values. Are they all different? And the answer is yes. That means this is a function. Now, the domain is going to include all the x values from the table. So we have -3, 0, 3, 5, close parentheses. And what do you see with the range? An interesting thing, they all have the same value. We only have one element in our set for the range, and that's 5. Perfectly okay. It's still a function because I don't care about the y's. I just check to see that all the x's are different. Now, we can have other ways of representing relationships. One of them is a graph, and so we see some examples of graphs here. If you'll notice on A, it's very similar to what we just did because we simply have 4 points that have been graphed on the coordinate plane. They all can be expressed as ordered pairs, and in fact we see those ordered pairs on the graph. So this should be easy for us to do. To decide whether or not it's a function, we check to see if all the x's are different. And you should notice we've got a problem here. Also, this pair, both of those have the same x value with different y's. That is why it will not be a function. We have x's that are repeated. Now, with graphs, you have another test you can use, which is very helpful to know. We call it a vertical line test. And that simply means if I were to draw a vertical line somewhere on this graph, would it ever cross through 2 points on the graph? Because if that were to happen, that tells me it can't be a function. And obviously I can see that if I were to draw a vertical line, x equals 4, it's going to pass through both of those points. So it's not a function. Now my domain, I only have 2 different x values in this particular graph. X could be -2 or +4. My range only has 2 values. The 2 y values that you see in these ordered pairs are 0 and 3. So A is done. Let's look at B, and here's what you will notice is different. This isn't just a few points that are on a graph. This is the graph of a line, and if you understand what a line is, if you go back to a definition you should have learned at some point, probably in high school, a line contains an infinite number of points. In other words, I can't list all the points that are on that line because any 2 points I think of, I can still find a point that exists between them. And if you'll notice at the end of these lines, you see arrows which indicate that it continues on. It's impossible to list all of the points. So we're going to have a new way of identifying our domain and range. We're going to cover that in just a second, but let's first answer the question, is it a function? So when I look at this, and remember I gave you an idea a minute ago with a graph, you can use what's called a vertical line test. If I were to draw a vertical line anywhere on this graph, could it ever cross my graph in more than one place? And the answer is no. As long as I have a graph that is linear, if this is a line, and when we say it's a linear graph, I'm excluding a vertical graph, and for now we'll say we exclude a horizontal graph. Those are actually constants that are graphed. As long as you see some sort of slant or slope to the line, it's going to be linear, and that means it will always be a function. And that is a very helpful thing to know. If you can remember that if you recognize that something is linear, it has to be a function, that will make life much easier for you. Not as much to have to think about in order to answer your question, you just know it. Now, in terms of answering domain and range, remember we can't list specific points here because there are an infinite number of points. So instead, we're going to use something called interval notation. Basically, that gives us a method for identifying, you might think of it as boundaries, for my x's are between, here's my first value and here's my last value. So anytime you see a graph and the points have been connected, it's continuous, such as this one with the line, then you will use interval notation to identify your domain in your range. Now, domain is x values, which means we want to figure out the point that would be furthest to the left on this line. Where would be the starting point from the left? Because if we're going to use interval notation, it has to be written from least to greatest. And so when I look at this, what I see is this line has this arrow down here, which means it keeps on going. Now what you have to recognize is although it appears to be pointing down primarily, is it also going to the left? And hopefully you will see that yes, it is. If I keep extending this line, not only is it going to continue to go down, but it will continue to move to the left. Is there ever going to be a point where it stops moving to the left? The answer is no. And if that's the case, and it goes forever to the left, we would say that it will extend all the way toward negative infinity. Now, infinity is not a number, it's a concept. In other words, it means that it's going to keep going forever, and if we use negative infinity, that represents that it's going forever to the left. That's going to be where x values begin. In other words, there's no boundary on it. The smallest number you can think of, it's going to be there. Now, when I look at the other end of this line that's drawn, I also see an arrow pointing not only up, but if I extend that, I need to recognize it's continuing to move to the right. So will there ever be a point that I get all the way to the right and there won't be any points further to the right on this line? The answer is no. It extends toward positive infinity as we go to the right. In other words, any number I could possibly think of is going to be in my domain on this line. If this line gets made large enough, eventually that point will show up on my graph. Now, remember I said we're writing this as if to show the boundaries. Well, there's something else we have to recall in order to know how to draw these boundaries correctly. So let me back you up just a moment and review something you might not have thought about since possibly even middle school. Let's look at how we would graph something like x is greater than 1. If I had asked you to graph that on a number line, you might recall that you would have had something that looked like this. And if all my x's should be greater than 1, I would come to 1 on this number line, and I would put a circle. And I know if I want numbers to be greater than 1, I want all the values to the right. So I would draw a line that goes to the right. And this would be the graph of all the x values that are greater than 1. Now you may recall as well, we had a decision we had to make about what type of circle to draw. I have drawn an open circle. And the reason I have is because in the inequality x is greater than 1, is 1 a solution? Well, the answer is no. 1 is not greater than 1. So if I want everything that's greater than 1, but I don't want to count 1, I use an open circle, which signifies this is the starting point, but don't include it. You just want everything that'll be to the right of this number. And the reason is, how would I know what the smallest number is next to 1? I don't. There's no way to figure it out. So by doing it this way, we're including everything that's to the right of 1, but we don't count 1. Now, if we're doing that in interval notation, we're not going to be drawing number lines, so we don't want to do open circles or closed circles. And by the way, a closed circle occurs if we had had an or equal to. And if that had been the case, then we would have colored in that circle to signify not only do we start at 1, but we include it because 1 is greater than or equal to 1. So we had open circles and closed circles on number lines. That means in interval notation, we need something to make the distinction as well. And what we will use will be open parentheses. And an open parentheses is the same as an open circle. It means we're starting at this value or this point, but it's not included. It's not really part of the answer. If we use brackets, that would be equal to a closed circle. So back to B, we're almost through with it. If we are trying to show in interval notation that our domain is every number we can think of, everything between negative infinity and positive infinity, the one thing we have to be sure we recognize is infinity is not a number. It's a concept. It's the idea that the number is going to go on forever. Since it's not an actual number, we don't want to use a bracket because that indicates that it would be or equal to, that it's included. So anytime you are using infinity or negative infinity, excuse me, when you're writing an interval notation, be sure you use a parentheses, not a bracket. Now for the range, we have to think in terms of the y values. That means we look at our graph from the perspective of down for the negative end, up for the positive end. Now this is probably easier to recognize because there's such a steep slope on this line. I'm pretty sure you can see that if I look at the bottom of this line, I can see it's going to continue to go down because of that arrow. The top is going to continue to go up as well. If there's not going to be a point where it stops either direction, then my range will be the same, negative infinity to positive infinity, closed in parentheses. If you will grasp this concept, linear equations will be very simple for you to answer the question, is it a function, what's the range, and what's the domain? Because this will be true for every single linear function. Remember, we're excluding vertical lines and horizontal lines. As long as there's some slope to it, this is going to be the answer for anything that's linear. Now, let's move to C. This is not a line, and in fact, we would say this is a closed figure. There are no arrows anywhere. This is actually the graph of an ellipse. You might look at it and say, well, that looks like an oval. The mathematical name for it is ellipse. And so if I were to ask you the question, is it a function? Remember, if it's a graph, try the vertical line test. I'm going to hope that as you look at this, you say, not a function. Cannot pass a vertical line test. Now, as far as the domain, I have to say where my boundaries are for the x values. And remember, it has to go from least to greatest. So as I move from left to right, the first point that I encounter on this graph is over here at this left edge of the oval. And remember, I'm thinking in terms of the x values. That is an x value of -5. You can count the spaces and you can see where it's marked on the graph, but I do not hit any point on the graph until I get to x equals -5. Now, if I were to track around the figure, remember it's a closed figure, all these points are connected. I have x values that exist all the way until I get where on the right side. My figure stops on the right side at +5. Now, I have to decide, should this be closed with parentheses or with brackets? If the point is included, you use brackets. If it's not, you use parentheses. Well, when I look at the graph, -5 is actually on the graph as well as +5. So we're going to close that off with brackets on both ends. As far as the range, you do the same thing, except be sure you go from bottom to top. It has to always go from least to greatest. So the smallest y value we see is -3. And we have graph that continues all the way until we get to +3. And again, because those are included, we close with brackets. One more example. Hopefully you recognize this shape. It's a parabola. That means the equation that formed it was quadratic. And the linear equations and the quadratic equations we will spend the most time on. So you want to notice some things that you can identify about quadratic equations that will be universal. That will really help a lot. Most of the time we will be looking at quadratic equations that either open up or open down. When that happens, that means that it came from the parent function y equals x squared. This one opens down. We're going to learn that means that there was a negative in front of the x squared. If it's positive, it will open up. If it's negative, it opens down, and we will get to that later. Right now, we're just looking at the graph, and if I were to ask you, is it a function? Hopefully, you can see that this does pass a vertical line test. That means it is a function. And if you pay attention to where these arrows are located and you consider extending this on, will you recognize that not only are both of these headed down, but the one on the left side is continuing to move left, the one on the right side is continuing to move right. If that's the case, what would be my domain? My x values would have to be from -infinity to +infinity. Those two pieces of information will always be the same for any quadratic equation that opens up or opens down. It'll always be a function, and your domain will always be -infinity to +infinity. Now your range is going to depend on which way it opens and where your vertex is. So when I think of this in terms of moving from bottom to top, the smallest y value, well, since this is going down forever, has to start at -infinity. And I see points continue on this graph until it reaches what y value? Well, the highest point on the graph is a y value of 4. Now you have to decide, is 4 included or is it not? It is. It's a point on the graph, so that one closes off with a bracket. So you can see with interval notation, it's possible to have both a parentheses and a bracket to identify a particular interval. Let's head to the next page. In terms of agreement on domain, I know we spoke about complex numbers in an earlier chapter, but we will have to remember that we are confined to the set of real numbers unless we have been told otherwise. So we're going to work simply with real numbers on this. We've already discussed the vertical line test. It means that if it intersects a graph in no more than one point, then your relation is a function. And because all of these graphs are identical to the ones that we just did, we went through all of this together, so we do not have to do it again. Now, this is the part that most students find to be the biggest challenge, and that is being given an equation without a graph and having to decide, is it a function, what's the domain, and what's the range. Now, if you recall, I told you the two most important types we need to become comfortable with would be linear and quadratic. Look at this first equation. It is linear. Now, here are some key things you recognize that makes it linear. First of all, I do not see any exponents on the variables. So that's got to be true if it's linear. I do not see any variables in the denominator or any variables being multiplied together. That would keep it from being linear. The third thing I would watch for is there are no special symbols. I do not see any square root signs or absolute value, anything like that happening to a variable anywhere. If those had occurred, it couldn't be linear. But since it meets the criteria that makes this linear, I already know if I graph it, it will be a line. I don't even have to know what it looks like when it's graphed. I just need to recognize it will be a line. It's linear. Therefore, is it a function? Yes, it is. And do you know the domain and the range? I hope so, because we just said a moment ago, as long as we know it's linear, our domain can be any x in the world. That means it goes from negative infinity to positive infinity. Be sure you close with parentheses. And your range will be the same, negative infinity to positive infinity. So if you recognize linear equations, that should be a simple problem for you to answer, as long as you've learned this. Now when you look at B, I'm hoping there's something about this equation that you recognize, and that's the fact that it is quadratic. Which part tells us it's quadratic? It's because it has an x squared, that x is the only variable that's squared, and that makes it quadratic. Again, we don't have any variables in the denominator. That would be a problem. But the x is squared, so that's going to make it a parabola that either opens up or opens down. Since what's in front of the x squared is a positive value, it's positive 1, that tells me this quadratic equation will open up. Now, since it's a parabola or a quadratic equation and it opens up, do I know it's a function? Yes, I do, because we've already learned as long as it is quadratic and it opens up or opens down, that makes it a function. Do I know anything about the domain? I should. There's not any number in the world that I cannot put in for x and square it. Any number I can think of is going to be on this graph for the x value. So from negative infinity to positive infinity, that will be my domain. Now the range will be a little bit trickier, because I will need to recognize a few things about this in order to get my range identified correctly. So here's what I know, and you might want to sketch a little graph to help you. If this had simply been y equals x squared, and there wasn't a plus 3 at the end, it would be a parabola that opens up, and my vertex would be at the origin at 0, 0. For right now, if you get one of these equations and you have to identify the range, if there is anything that will change from that, if it's got something else involved besides y equals x squared, it will be similar to this, where there will be a number that's either added or subtracted at the end. And what we're going to learn as we move a little further in this chapter is that identifies where the vertex is located, if it's shifted up or it's shifted down. If it says plus 3, that tells us that parabola that opens up is moved up 3 units, and if we were to kind of look at a quick graph of this, what you would see is something that would be very similar to that. The parabola opens up, but the vertex would be right here at the point 0, 3. Now, what we will do is write that range. Remember, you go from bottom to top. So the first value that I would encounter is 3, and I realize my drawing is a tad off. I kind of missed the mark there. My stylus is a little fat, sorry. But 3 is included because that's where my vertex is, so it needs to have a bracket. And all of the y values go up from there. So from 3 to positive infinity, that would be my range. Now, as you look at these last 3 examples, they're a little trickier, and this is where you're going to find you have to do some analysis. You're going to have to think through. X equals the absolute value of y. Now, our goal in trying to decide is it a function is we want to know, is it possible for the same x to get more than one y? Because if that happens, I know it's not a function. If I'll only get one y for every x, then I've got a function. And you may or may not know what this graph looks like. So instead of approaching it the way we just did the other two, because we knew what those should look like, we need to consider some options in deciding, first of all, whether or not this is a function. So what I'm going to recommend in a case like this, see if you can come up with what we would call a counterexample to show that it couldn't be a function. And if I can't come up with an example that proves that it's not a function, then hopefully that means that it is, and I didn't just happen to overlook the example that would have shown me that it's not. So what we want to do is look at this and let's think about what values we could have for x. Now, you need to know what absolute value means. Absolute value means the actual distance that whatever is inside that absolute value bar, the distance it is from 0 on a number line. Now remember, distance is always a positive value. You can't have a negative distance. So that means x is going to need to be a positive number, because when I take the absolute value of something, I'm going to get a positive number. So let's say that x is 3. Okay. If that's true, then I want to see what I could come up with for a value of y that would be a solution for this. Well, I definitely know that if I take the absolute value of positive 3, I get positive 3. So that tells me that the ordered pair 3, 3 is going to be a solution. When x is 3, y can be positive 3. But is there anything else that could work? Well, if you think about it, positive 3 means you went 3 units to the right of 0 on the number line. Couldn't I also go 3 units to the left? I sure could. And that would mean negative 3 could also be a value for y that would make that true. I just found a pair where I have the same x and 2 different y's. What does that mean? It means it's not a function. Now, there are other ways you could determine whether or not you have a function, but that, to me, is a logical approach. See if you can come up with a counterexample. Now that we've done that, let's see if we can identify the domain and the range. Now, remember, domain is listing all the possible values you can have for x. Oftentimes, I think it's helpful to think of this in terms of the types of values you could get. If you think of it as, can I get positives, can I get negatives, can I get 0? That oftentimes will help you sort of figure out what you should use for your domain or range. So look at those x's. Remember, we said it's what you get after you take absolute value. Can you get positives? Absolutely. That's what you're going to get when you take absolute value. So I know all the positive numbers should be in my domain. Is it possible to get negative? No. We said if I'm taking the absolute value, it can't be a negative number because distance is always positive. So the only other question is, could it be 0? Well, if I was taking the absolute value of 0, then yes, the distance is 0. So 0 and the positive numbers have to make up my domain, which means I'm going to go from 0 to positive infinity, because infinity is a concept. I know it needs a parentheses. Now you have to decide, does 0 need a parentheses or a bracket? Did we say 0 was included? Yes, we did, so we use a bracket. Now ask yourself about the range. The range is the y value. It's what we're putting inside the absolute value bars. Can I put positive numbers inside? Yes, I can take the absolute value of positives. Can I take the absolute value of negatives? Yes, I can. Can I take the absolute value of 0? I certainly can. There's not any value I can't put inside the absolute value bars. So that means my range has got to be negative infinity to positive infinity. Now, don't get too frustrated, because there is a lot of analysis that goes with this, and the more you practice, the better it gets. Look at example D. Here's what I hope you will notice. If this inequality was not here, the greater than or equal to sign, and it just said y equals negative x, hopefully you'd know, hey, this thing is linear, and you would know exactly how to answer everything. But the inequality makes something a little bit different. For example, if I were to graph, and I'm going to come up here where I have a little bit of space, y is greater than or equal to negative x, here's what I would see. If I were to plot the line y equals negative x, and I'm going to do that because, again, I need to know where this line is. If it were y equals x, I know 0, 0 would be on the line. If x were positive 1, then that would mean y is negative 1. If x were negative 1, that would mean y is positive 1. And what I have is a line that passes through these points. Because it's or equal to, it's a solid line. The only thing that would be different if the or equal to was not there is typically we would graph it with a dashed line, which shows it's the same concept as the open circle. It shows this is the boundary, but don't count it. The greater than part, though, means I want everything above the line to be included. So probably at some point you have seen these graphs where you have this that's shaded. Now, that means everything that's in the shaded area and the line are all included as part of the solution. So when you go to answer the question, is it a function? You need to ask yourself, will it pass a vertical line test? Absolutely not, because everything that's shaded is a solution. It's going to pass through an infinite number of points when I draw a vertical line. That means anytime I see an inequality, it is not a function. And that would be helpful to know, because if there's an inequality, there's shading somewhere. And if there's shading somewhere, it's not a function. Now, as far as the domain, notice that it includes the line and everything else that's shaded. I already know just the line itself has a domain from negative infinity to positive infinity, as does the range. So if this had been something that would have been linear, but it includes the shading, that doesn't change my domain or my range. The only thing it changed is with the shading, I no longer have a function. One more example. What we have now is an equation y equals 3 over x plus 2. Be careful as you look at this. Would it be linear? I hope you say no, because I see a variable in the denominator. Remember, if we have a variable in the denominator, it can't be linear. This is actually called a rational equation. Okay? And when it's a rational equation, that means because of that variable in the denominator, we've got some values that will be excluded. Now, in terms of deciding if this thing is a function, remember, part of the idea is if I were to choose something for x, can I get two different y's back? And if I look at this, it may seem a little bit confusing because of the fraction, but basically, if I put in 1 for x, Then 1 plus 2 is 3. That would be in my denominator. 3 divided by 3 is the number 1. That is a single value. If I put in 1 for x, I get back 1 for y. I don't get a second number back. And if I test a few more, I'm going to quickly see I can't get two different y's from using just one x. This will always be a function when it's a rational equation. Now, the trick is knowing what to watch for in identifying domain and range. The domain is the possible values I can use for x. Because x is in the denominator, you need to remember a denominator in a fraction can never have a value of 0. That's undefined. It's impossible to divide by 0. So if I look at this denominator, what value of x would cause the denominator to be 0? In other words, set x plus 2 equal to 0, and that's going to tell you where your problem is. It's at -2. So I need to figure out a way to say I can use any x I want except I cannot use -2. Here's how you do it with interval notation. We would include everything from -infinity to -2. But now remember, we don't want to count -2, so we close it with a parentheses. We're going to use the union symbol. That's a capital U. And then we need to include everything that starts at -2 and goes to positive infinity. And again, we don't want to include -2, so we use parentheses there as well. That's how we can say our domain is everything except we don't use -2. Now for the range, this one's a little bit trickier. You've got to think back to what values can I get for y. So y is equal to this entire fraction. And the only problem, I know I can get positives back. If I put in, for example, +1 for x, if I'm putting in positive values for x, I'm getting back positives for y. If I were to put in a negative value for x, like -3, -3 plus 2 is a -1, and 3 divided by -1 gives me a -3. So I think I can get positive numbers, I can get negative numbers, but can I get 0? What is the only way a fraction would be equal to 0? Only if I have 0 in the numerator of the fraction. And look at this fraction. It has 3 in the numerator, no variable. There's no way to ever turn it into 0. This fraction can never equal 0. That's the one value that will be excluded on my range. So it's going to look just like the domain, except I'm going to change the -2 to 0. And now I have my range written. Okay, let's go to the next page. I know this is a long